going to go over multiple numerical integration approximation formulas. And I want to approximate for this the integral between 1 and 3 of the natural logarithm of x squared dx. And I have the actual answer here on the top. So I first rewrote the natural logarithm based upon the power rule property of logarithms to be the integral between 1 and 3 of 2 times the natural log of x dx. Using integration by parts, this makes 2 times the natural log of x times x minus the integral of x times 1 over x dx. And that just becomes 2x times the natural logarithm of x minus 2x. And we are going to evaluate this between 1 and 3. So, doing so, if we were to put that into a calculator and all those parts, we would obtain an answer of exactly 2.5917. So, something to keep in mind as we go through some of these examples. So, the trapezoid rule. The trapezoid rule. This, based upon the equation here that we have, this is going to be the integral between 1 and 3 of 2 times the natural logarithm of x dx. We are going to approximate this by taking h over 2 times y sub 0 plus y sub 1. So, because we have our bounds between 1 and 3 here, h is just going to be 3 minus 1, or 2. So we have 2 divided by 2 times, this is going to be 2 times the natural log of 1 plus 2 times the natural log of 3. We put that into a calculator and we would get an answer of 2.1972, which is a bit off from the actual answer. The second one I have here is Simpson's rule. So this approximation of the integral between 1 to 3 of 2 times the natural log of x dx, this will be approximated by h over 3 this time times, this is going to be y sub 0 plus 4y sub 1 plus y sub 2. And that is going to be, for this case, h for this particular one is now going to be 3 minus 2 to get us an answer of 1. So this would be 1/3 times 2 times the natural log of 1 plus, this will now be 4 times 2, so 8 times the natural log of 2 plus 2 times the natural log of 3. When we toss this entire thing into a calculator, we would get an answer of about 2.5808, which is closer, a lot closer than this trapezoid rule. Still not that close, unfortunately. The composite trapezoid rule. Let's move this down slightly so I have more room. Okay, composite trapezoid rule. So, we're trying to approximate the integral between 1 and 3 of 2 times the natural log of x dx. And this is going to be approximated by, let us see, h over 2 times, so for this we are doing y sub 0 plus, we are going to be using a total of 4 panels. So This is the composite trapezoid rule. We are using 4 panels. So, plus y sub 4. And then we're going to have plus 2 times, this will be y sub 1 plus y sub 2 plus y sub 3. We are using 4 panels, so we were going to have for our step size h, we are going to have 3 minus 1 over 4, which makes 2/4 or 1/2. So just to write what this is going to be 1/2 divided by 2 times, this should be 2 times the natural log of 1 plus 2 times the natural log of 3 plus 2 times. Plus 2 times. And now this is going to be 2 times the natural log of 1.5. And let me just fix my L as I kind of smushed that into there. Didn't really make it too legible. That's a bit better. 2 times the natural log of 1.5. So we just added the step size of h to the value of 1 to get 1.5. That should be plus, now it's going to be 2 times the natural log of 2. So again, we add the step size h to 1.5 to get 2. Plus 2 times the natural log of, this is going to be 2.5. And once again, we would add the step size of h to this 2 to get the 2.5. If we put this entire thing into the calculator, we would get an answer of about 2.5642, which is not as good of an approximation as the Simpson's rule here, but closer than the regular trapezoid rule, and a decent approximation of the actual answer. We now have the Composite Simpson's rule. Again, we are going to use 4 panels. So, this one's going to be a bit of a long formula, so bear with me. We're doing the integral between 1 and 3 of 2 times the natural log of x dx. We are going to approximate this using this particular formula of h divided by 3. H divided by 3 times, this is going to be y sub 0 plus y sub 8, since we're using 4 panels, plus 4 times, this would be y sub 1 plus y sub 3 plus y sub 5 plus y sub 7, plus 2 times, this is going to be y sub 2 plus y sub 4 plus y sub 6. And I need a bracket here. Okay. We are using 4 panels. H is going to be 3 minus 1. This will now be over 8, since we have 8 panels. Well, we have 4 panels, but based on the formula, this is going to be 2 times that number of panels, so 8. Doing this out, we get an answer of 1/4. So, the actual formula, when we break this up, again, bear with me, it's a long one. 1/4 divided by 3 times, This would be 2 times the natural log of 1 plus 2 times the natural log of 3 plus 4 times 2 times the natural log of 1.25. So adding h to 1 plus 2 times the natural log of 1.75 plus 2 times the natural log of 2.25 plus 2 times the natural log of 2.75. So that's where all of our additional sections are from using the panels. I do, however, need to add one additional space here, or a couple. Might be a better idea to look at, since, as you can see, we're going to run out of room fast. This will now be plus 2 times the natural log, and I forgot the additional 2, 1 second, 2 times the natural log of this would be 1.5 plus 2 times the natural log of 2 plus 2 times the natural log of 2.5. If we were to put this entire thing into a calculator, you would get an answer of 2.5916, which, as you can see, is better than the composite trapezoid rule and the regular Simpson's rule. The actual answer was 2.5917, so pretty close. I got 2 more here. So, the midpoint rule. Midpoint rule. This one's going to use an h of 3 minus 1, or 2. So, this integral between 1 and 3 of 2 times the natural log of x dx, this approximation just takes the form of h times the midpoint, which will be, and actually I shouldn't call that w. W is the midpoint. We need the evaluation of the function at that midpoint. I'm just going to call that w for this. Yep, that works. So w takes the initial value that we had of 1, and we are going to add to that simply just 1 to get to the midpoint value of 2, since 2 is halfway between 3 and 1. This is going to be 2 times, well, simply f of 2. So 2 times 2 times the natural log of 2. A lot of 2's. Tossed into a calculator, we would get an answer of 2.7726. And that's the first formula that kind of overestimates the actual integral. But that's the midpoint rule. For the composite midpoint rule, this one's going to use an h of 3 minus 1 divided by 4. So 1/2. And again, we are going to be using 4 of these midpoints. Hence where this comes from. So this is going to be the integral between 1 and 3 of 2 times the natural log of x dx, and we are approximating that by this formula of h times, and this is going to be f of w sub 1 plus f of w sub 2 plus f of w sub 3 plus f of w sub 4. In this case, that's going to be 1/2 times. So, for these midpoints, this is going to be 2 times the natural logarithm of 1.25. And that's due to the fact that we're basing this on 4 midpoints. So if we look at the original sectioning of 4 panels, so I'm just going to put here 4 panels, that used the values of 1, 1.5, 2, 2.5, and then 3. So we're taking halfway between 1 and 1.5 to get 1.25 plus 2 times the natural log of halfway between 1.5 and 2, so 1.75 plus 2 times the natural log of halfway between 2 and 2.5, which was 2.25. I am running out of room, so I'll just write that down here. Plus 2 times the natural log of halfway between 2.5 and 3, so 2.75. Toss that entire thing into a calculator, and you get an answer, a closer answer at least, of 2.6053. So those are several approximations of the integral based upon those numerical integrations. Thank you.